Hello and welcome to part one of our revision session on circle theorems. In part one, we are going to look at introducing all of the circle theorem rules and see how they can be applied to a series of examples. However, before we start with that today, I just thought I would test you on some other angle work with a same surface, different deep starter activity. So I'd like you to look at these four very similar looking diagrams and see if you can answer each of these. Try and do some working out for every single question, please. And I would pause the video here because I'm going to go through the answers. So I'm going to start with the question in the top left corner. I've made myself a little bit of room. It says the diagram below shows a straight line. Find the value of x. Well, because it's a straight line, we know the angles on a straight line add up to 180. So we can make an equation here. We have the two angles, 2x and 6x. So 2x add 6x must equal 180. So 8x equals 180. How we're going to find x? We need to do 180 divided by 8. And 180 divided by 8 is 22.5 degrees. One way that you could do that is halve it, 90, halve it again, 45, halve it again. So x is 22.5. Moving on to the question in the top right corner, it says the diagram below shows the vertex of a polygon whose interior angle is marked. Write an expression for the exterior angle. So what you need to imagine here is this is the corner or the vertex inside some polygon, and this green part represents the exterior angle. Now we know that an interior angle and an exterior angle add up to 180. So let me call this x. I can work out x by doing 180 take away the angle that I already know, which is 3y take away 40. So this becomes 180 take away, this is like multiplying this bracket by -1. So it becomes minus 3y, and subtract -40 becomes a plus 40. And I can add these two numbers together. So it is 220 take away 3y. Now moving on to the bottom left, it says the diagram below shows the vertex of a regular polygon whose interior angle is marked. How many sides does the polygon have? Well, some of you might recall that the easiest way of getting to the number of sides of a polygon is actually through the exterior angle. So if I know the interior angle is 168, I can work out the exterior angle by doing 180 take away that. And 180 take away 168 is 12 degrees. I'm then going to use the rule that says the exterior angle is 360 divided by the number of sides. And if I rearrange that, I can get the number of sides is 360 divided by the exterior angle. So I just need to do 360 divided by 12, and that is 30 sides. Finally, looking at the bottom right, the diagram below shows the interior and exterior angles of a regular polygon. The angle marked B is 4 times the size of angle A. What is the name of the polygon? So then, angle B must be the interior angle, and we are told that angle B is 4 times the size of A. So I could also call that 4A. So now I'm going to use a little bit of the maths that we used in that first question, because A and 4A, 5A, must equal 180. Dividing through by 5, A must equal 36. Then using a little bit of maths from the previous question, the number of sides is 360 divided by the exterior angle. So the number of sides is 10. What do we call a polygon with 10 sides? That is a decagon. So here we are with circle theorems. Over the course of the next few minutes, and this video might go on for a little while, we are going to be looking at all the rules associated with circle theorems. I think I have it down to 6 rules that we are going to use. When we studied circle theorems, we will have probably spent at least one lesson on most of these rules. So we're probably looking at a topic that took 5 or 6 lessons minimum. So I'm going to go through all the rules in this one video, and then in part 2 of the revision, I'm going to be explaining why these rules work. So rule number 1, we also called it, or I certainly refer to it as the Star Trek badge, is the angle subtended at the centre by a chord is twice the angle subtended at the circumference. And a lot of you remember this from the shape, which is this arrowhead design. It doesn't always have to be an arrowhead. It depends where these 2 corners are, but traditionally we see it as an arrowhead shape. And we have this angle here at the centre being twice the angle at the circumference. So if you've been able to print out these sheets, great, because then you won't have to draw any diagrams. We can very quickly go through a couple of examples. So how are we going to work out angle W? We'll always populate any angle diagram, and this goes for triangles, quadrilaterals, polygons, with any angles that you know. Now I can work out that angle using angles on a straight line. Obviously we'd normally show a lot of working out. I'm going to do a lot of this very, very quickly today. So that must be 52. And that was using angles on a straight line, subtracting from 180. So W is 2 lots of 52, which would make it 104 degrees. Now, the diagrams can be a little bit more complicated than that. And because we're dealing with a circle, if we see this second example, I've got 2 radii. Now, both those radii are the same length. So quite often you will have some embedded isosceles triangles to look out for. So that is how we're going to work out angle Y. We can do 180, take away 106, and then halve it equally to work out Y. Well, 180 take away 106 is 74 degrees. Divide it by 2. And that is 37 degrees. Of course, angle X is just going to be half of the 106 because we are using rule number 1. So angle X is 53 degrees. Now, sometimes in the question, it might say give a reason as to why. If you write the reason, Star Trek badge, you are not going to get the marks, I'm afraid. That is just a nice way of remembering it. You would have to argue that the angle at the centre is twice the angle at the circumference. Rule number 2. And we'll see in Circle Theorems part 2 why this is an extension of rule number 1. But the angle subtended at the circumference, if we have a diameter, is always 90 degrees. So look for the fact that you have the centre of a circle. Is that marked on your diagram? Because unless you're told you've got a diameter, if they do not mark the centre of the circle, do not assume it is a diameter. So let's have a look at this quick example. This time I thought I'd go for a little bit of algebra. So if that angle is 90 degrees, because I have a diameter, and the angles in a triangle add up to 180 degrees, so we're still using some very basic angle rules, we know that the x and the 4x, the 5x, must total what is left. Well, there's already 90 degrees there, so it has to be 90. So to work out x, it's 90 divided by 5, which is 18 degrees. Rule number 3, we had lots of names for this, the bow tie, the butterfly, but I'm still keen on Mr. Underwood's bunny ears. I don't know if he owns a pair of bunny ears and that's why he came up with this name. But the angles in the same segment are equal. And what we mean by that is this diagram here. If you have 2 points, sometimes there's a chord drawn in, and you have 2 points joined to those on the circumference, then those 2 angles are equal. So if we look at this diagram here, we can immediately see another angle that is the same as 19. It is that one there. Similarly, this angle has to be 48 degrees. So I can now work out angle A using angles in a triangle. They must add up to 180. So if I work out what 19 add 48 is, and subtract it from 180, while 19 add 48 is 67. If I subtract that from 180, angle A is 113 degrees. For my second example, we've got a little bit extra going on. I've brought some parallel lines in, so we can just drop that angle notation in a moment. But I can see using angles on a straight line that this angle here must be whatever is left from 180 degrees. And 180 take away 124 is 56 degrees. So this angle is 56. B is also 56 degrees because of our rule. These 2 angles are the same. But C is also 56. Can you see why? Do you know what that is called? So there's my parallel lines. Yes, it's a Z angle, but remember Z angles wouldn't get you the marks. That one was called an alternate angle. So your Z is an alternate. The F shape was called corresponding. Rule number 4 is to do with cyclic quadrilaterals. Now this one has an official name, so this is quite often one that they will get you to explain in words because it isn't quite so difficult to remember. You've just got this phrase cyclic quadrilaterals. And the opposite angles in a cyclic quadrilateral have to add up to 180. They're not the same, they add up to 180. It has to be all 4 corners, all 4 vertices on the circumference of the circle for this to work. So, if we have a quick look at our example, these are opposite. These must add up to 180. A is 88. These are opposite. These must add up to 180. So B is 97. Obviously, I'm going through this quickly. We could show some working out. With this other question, I've put some little whiskers in. So remember, that means that this shape is an isosceles triangle, which means that this angle in the isosceles triangle and this angle are the same. Well, I can work out this angle first using the fact that the opposite angles have to add up to 180. So this angle here must be 32 degrees. So how can I work out C? Well, I can do 180, take away 32, which we incidentally already know, but then I need to share it equally between 2. So C ends up being 74 degrees. Rule 5 is quite an interesting one, and it's to do with tangents. And the angle between a tangent and the radius where that tangent touches the circle is always 90 degrees. And included in this one, we're actually getting 2 rules for the price of 1. The length of the tangent from a point is always the same. So what I mean by that is if we have a point and a tangent touching a circle on one side, a tangent touching the circle on the other side, these two lengths are the same. Now with questions like this generating a 90-degree angle, you could also introduce some Pythagoras questions, you could introduce some trigonometry questions. I'm doing a relatively straightforward example here, so let's see what we've got. Both of these must be 90 degrees. These triangles are actually congruent. Because these lengths are the same, the angles must also be the same. So this is the same as angle A, this is the same as angle 15. So I can just use angles in a triangle here to work out A, and A is 180, take away 90 and 15. So it's the same as 180, take away 105, which is 75 degrees. Our final rule for today is the alternate segment theorem. So that again, this is another one that has an official name. So this is quite often a question that you might have to explain why you know angle A is what you are saying it is. And this one says the alternate segment theorem states angles in the alternate segment are equal. You must have a tangent for this question. So if you don't have a tangent, you are never going to have the alternate segment theorem. So what the alternate segment theorem says, if you have a tangent and a triangle embedded in a circle, then these two angles are the same, and these two angles are the same. Why is it called the alternate segment theorem? Well, this chord, where A is, chops this circle into two segments, a minor segment, remember a segment's a piece of an orange, and a major segment, and you could argue that these angles are in the opposite segments of each other. So let's have a look at one example. What we have here is a tangent, we have our embedded triangle. In fact, we actually have two triangles. But what I'm looking at is angle A, and angle A is the same as 78 degrees. And that is just using the alternate segment theorem. If you're interested in a proof of the alternate segment theorem, you will see that in our next revision lesson. How are you going to work out angle B? Well, we're going to use a combination of some of our previous rules. We have two radii, so that little triangle must be isosceles. A couple of different ways that I could approach this question. I could work out this angle here by using rule number 1, and this would be double 78. However, I'm not going to do it that way because I think there's an easier way. Because this is a radius and this is a tangent, all of this angle must be 90 degrees. I can work out this tiny sliver of an angle and it will be the same as angle B. So B is just 90 subtract 78 degrees, which is 12 degrees. Now there are a series of questions for you to try today. I have some level 1, some level 2, some level 3 questions, so do go back to my instructions and have a look at which questions you would like to try. I've done worked solutions for every single set of questions, so do check the questions that you have tried. If you can't see why an answer is as it is, then please do not hesitate to get in touch. You can ask questions in the Ask the Teacher channel.